So let's go through what we've learned already with this average rate of change and instantaneous rate of change and tying this to the idea of the derivative. So average rate of change, or it's the same thing as the slope of a secant line. So if we're looking at some interval a to b, maybe not there, let's do here. And we use the two coordinates on our function. So we have the coordinate a, f of a, and the coordinate b, f of b. The secant line would connect those two together. And I just want to make sure I get this right. Something like this. So that line right there is the secant line. And this average rate of change comes from the slope between those 2 points. So the slope of the secant line over a to b is the average rate of change. Or for short, we call it AROC. And what we do is we take the difference in the outputs over the difference in the inputs. So we end up with this f of b minus f of a over b minus a. So that's our average rate of change. But then this new idea we're getting this term is the idea of the instantaneous rate of change. So this happens at a single point. So we're looking at just one coordinate, and we're looking at the tangent line at that coordinate. So let's say we were here at -2, 4. And if we took the instantaneous rate of change at that point, what we're trying to do is draw a line that matches the slope perfectly at that point. So right around that point, we're starting to see a line like this. So what we should get with this line, and this is what we're going to talk about actually calculating this time, because in the last week, we just tried to visualize it as best we could, but because I know calculus, I know that this is going to have a slope of -4, so I'm just going to draw this, and there's our tangent line. So the line matches up so that it just goes through that coordinate right there, and then it's matching the slope right at that point too. So we're getting this tangent line. That's what we're graphing here. So that is the tangent line. And the slope of that tangent line is our instantaneous rate of change. So how we want to talk about this, because we're trying to talk about slope at just a single point, so let's call this our x value. What we want to do is talk about how our slope is changing with a second point. Let's say I call it here with x plus h. So what that would do is it would grab a point here and we'd find our secant line. And then what we want to do is have h get closer and closer to, we basically want h to be 0 so that we're on top of that coordinate, so that we're just graphing a secant line right there. But we can't do that because if our change in inputs is 0, so let me go to my secant line here. So if these numbers are the same, we'd have 0 in the denominator, and then that's undefined. So we want to have just a little difference. So what we're doing here is looking at that difference in outputs, and really this is the difference in inputs. So the input of x plus h minus x, but x minus x will just leave us with that h there. And what we want to do is evaluate this as h approaches 0. Now notice we can't just plug in 0 here. We can't do that direct substitution because we can't have 0 in the denominator. But what we want to do is basically look at, as this gets closer and closer, what is our slope? And that gives us our slope of the tangent line. So this right here is called the difference quotient. The difference quotient. And this gives us many things. It gives us the slope of the tangent line. it gives us the instantaneous rate of change, and it gives us what we call the derivative. That's what we're getting at here. So what we're coming across are just so many names for the same thing. It just kind of depends on what context we're looking at, but really they all calculate the same thing. So the derivative is the slope of the tangent line, is the instantaneous rate of change at a point. Those all tie together with each other. So for the derivative, we use this notation. So we have f with kind of an apostrophe of x. How we read that is f prime of x. But this is describing the derivative of f of x. Derivative of f of x. dy dx, this next notation is the same idea. It's kind of like our different notation. This is our function notation. So like if we had a line, what we've done before is if we used function notation, it's f of x equals mx plus b. If we just used an equation, it would be y equals mx plus b. That's kind of the difference in this notation here. This is using function notation, which is really what we use a lot of the time. Sometimes this notation is helpful too, but this notation kind of applies to this equation setup. And how we would read this is the derivative of y with respect to x. Really, that notation becomes helpful when we start kind of switching up our variables, but that's really more in calculus 2. This m with the subscript of tan just means slope of the tangent line. So m is our slope notation, tangent line to denote specifically where that slope is coming from. And then right here is that same notation for the difference quotient. So evaluating this limit here is going to give us the derivative, is going to give us the slope of that tangent line. So all of those ideas together. Okay, so what we're going to do is let's apply this, see how it comes together, focusing on if we want to find the derivative. And with this video, we're going to focus on the derivative at a specific value. We're going to focus on using this difference quotient. Now, as you can tell, there's going to be some things to input and evaluate and simplify. There's going to be lots of steps to this section. And next week, you might be a little bit frustrated because next week we're going to get a bunch of shortcuts. But before we can use the shortcuts, we need to see why the shortcuts work. Where are the shortcuts coming from? And it's all coming from this difference quotient. So this week we're going to focus on kind of the long algebra of it, and we pay our dues, and then we can rely on those shortcuts next week. Okay, so let's say we have a function, 3x squared minus 4x plus 1, and we want to find f prime of 2. Or we could say the derivative of f at x equals 2. That's what we're trying to find here. What that also relates to is if we are at x equals 2, what's the slope of the tangent line? All of those pieces come in. And actually, let's write those down as we're getting used to this idea of the derivative. So we have this function, so f prime of 2, this is the derivative of f at x equals 2. It is also the slope of the tangent line at x equals 2. So the idea being, if we graphed out this function and went to x equals 2 on our graph, we're trying to look at that tangent line and the slope of that tangent line. But what we're going to be able to do here is actually calculate it rather than trying to guess from the graph. So to do this, f prime of 2 is equal to evaluating our difference quotient. Now, what's going to happen here is we're going to try to evaluate this as h is approaching 0. Where we have x, we have a number to plug in. We're going to be plugging in this x equals 2. So what we want to do is evaluate this limit as h approaches 0 of f of x, which we're letting be 2 in this case, plus h, minus f of 2 all over h. And eventually I want to try to plug in h equals 0. I don't want to do it yet because that denominator would just turn into 0. So instead what I want to do is I want to simplify this numerator. I want to simplify this f of 2 plus h. I want to simplify this f of 2. And I'm going to do this work off to the side. In fact, I'm going to go to a different page because I didn't leave myself much room here. But basically, I want to use this function 3x squared minus 4x plus 1 to evaluate these two pieces. So I'm just going to go to a fresh sheet of paper here and write down that my function is that 3x squared minus 4x plus 1. And we want to evaluate two things. Actually, let's do f of 2 first. And then let's do f of 2 plus h. So f of 2, we're plugging into our function. So 3 times 2 squared minus 4 times 2 plus 1, which is 3 times 4 minus 8 plus 1. So a 12 minus 8 plus 1. So we got a 4 plus 4. So we're getting 8 out. So what we just did is we found a substitution for f of 2. We can now just substitute the value 8. All right, f of 2 plus h, we want to make a substitution as well. So our function tells us we have 3 and then our input squared minus 4 times our input plus 1. And in this case, our input is this expression 2 plus h, 2 plus h. All right, let's get some good old algebra review. 2 plus h squared. The most common mistake is switching this to 4 plus h squared, and that is not correct. What we need to do is remember that 2 plus h squared is the same thing as 2 plus h times 2 plus h, which means we have a binomial multiplying a binomial, which means we need to FOIL. This is going to be it's called a perfect square trinomial. So if that sounds familiar, if not, that's fine. But just a reminder that when we square an expression, we should actually be ending up with 3 terms at the end. So multiply first, 2 times 2 is 4. Outer and inner, so we're going to have 2h plus 2h, so we're going to have a plus 4h. And then last, h times h squared. So equals 3 times, and where I have this 2 plus h squared, that would simplify to this 4 plus 4h plus h squared. And then with that negative 4 times 2 plus h, we need to distribute. So we're going to have a negative 8 minus 4h, and then that plus 1 at the end. All right, next step, distribute 3 into that trinomial. So 3 times 4 plus 3 times 4h plus 3 times h squared minus 8. Ooh, let's go ahead and combine those like terms. So minus 8 plus 1, so that's a negative 7 minus 4h. All right. Last step, combining like terms. We have 12 and the negative 7. We have the 12h and minus 4h. And I'm just going to put this in standard form. So we're going to have 3h squared. 12h minus 4h is a positive 8h. And then 12 minus 7 is a positive 5. All right, so we're going to make this substitution where in my function, I saw f of 2 plus h. I'm going to substitute this 3h squared plus 8h plus 5. So I'm going to come back here. We're still doing the limit as h approaches 0, so don't leave that notation off because that's important to our evaluation. And we'll have 3h squared plus 8h plus 5. So that's our first expression. And then we're subtracting f of 2, which we got as 8. Ooh, and if you've been cringing this whole time because I did that wrong, you are correct somehow. I did that thing where my mind was already working on a calculation and I was it's hard to talk and do math at the same time, and I've made a career out of it somehow. So let's try that again. 12 minus 8 is 4, and then it's a plus 1 at the end, so that should be a 5. Okay, luckily caught it before we did too much more. So we're going to have a minus 5 here. I'm actually going to just drop those parentheses, and then we'll have all over h. So now I have something I can start simplifying. So in here, positive 5 minus 5, that just turns into a 0. So those just kind of cancel out with each other. And then we have a common factor of h, which is exactly what we want to have here, because again, I just don't want that h in the denominator. So let's see, I can take out 1h from here, so we're just left with h1, and then where we have 8h, that would just cancel out and leave no h's behind. So now h has divided into everything that's left over. So this is the same thing as the limit as h approaches 0 of 3 times h plus 8. And now that we don't have our denominator anymore, now we can plug in h equals 0 because it will be defined now. So now to take care of that limit, we're going to go 3 times 0 plus 8. We can drop that limit notation as soon as we're plugging in h equals 0, and it is 8. So f prime of 2 is equal to 8. And let's go and check that out on a graph. So let's go to Desmos and see what is this telling us. So what I'm going to do is graph. I'm going to graph our function. Let's see. I'm going to call it f of x equals 3x squared minus 4x plus 1. We're looking at the coordinate 2, f of 2. So we can see our parabola. We can see the coordinate that we're looking at, which is the coordinate 2, 5. And what we're trying to do here is finding f prime of 2 is the same as finding the slope of the tangent line here, or that instantaneous rate of change. Now I can tell visually that it's pretty steep and positive, so 8 is feeling right. What we could do is verify it. What I'm going to do is draw a line here using the point slope form. So we take y minus our y coordinate, which was a positive 5, equals our slope, which we calculated that to be 8 from that derivative, and then in parentheses, x minus the x coordinate, which is 2. And now we can see our tangent line, which means our slope is correct. Say we took the derivative and it came out to be 6. Oh, that looks kind of weird right there. Especially if we zoom in, it seems like we're missing it. But as soon as we go to 8, that's matching so nicely around that coordinate, which is exactly what we want to see. So all of that work of evaluating that difference quotient, a lot of textbooks and videos will do all of the work within the difference quotient here, and that is completely fine. I just kind of like separating out my work and organizing it this way, but either way is completely correct for showing your work for this. Okay, I know this video is getting long, but I'm going to go through another example, and this one's a lot simpler. Still steps to do, but it's a simpler function to work with. So we want to find the equation of the line tangent to the graph of f of x equals x squared at x equals 3. So with this one, we want the equation of the tangent line. So we want to end up with y equals mx plus b. So to do this, we need to find the slope, and that slope is going to come from the derivative. So the m is going to equal the derivative of our function f at x equals 3. And then we could find b by plugging in a coordinate. We can get a coordinate, let me make little notes to myself. So to find b, plug in the coordinate 3, and then our function is x squared, so 3 squared is 9. So there's just some side notes of how we'll eventually get our function. Basically, our big piece is to find this derivative of f at x equals 3. So f prime of 3 is equal to the limit as h approaches 0 of f of x plus h, or we're letting x equal 3. So this is 3 plus h minus f of 3 all over h. So now I'm going to go do that side work. Maybe I'll show you this one with all of the work in one, just so that you can see it, especially to match other resources. And this one isn't too bad to do all together in the notation, just so you can see it. But if you like that separation of the work, that works great too. Okay, so with this one, I'm going to keep that limit notation because it is very important to keep the idea of evaluating the derivative. F of 3 plus h, so we're plugging 3 plus h into our function x squared. So we're taking our input squared, and our input is 3 plus h. And then we're subtracting f of 3, so taking 3 and plugging it into x squared, so 3 squared, all over h. So that equals the limit as h approaches 0. Then what I'm going to do is evaluate that 3 plus h squared, which again should be this 3 plus h times 3 plus h. So we need to FOIL, and that should come out to, let's see, 3 times 3 is 9. And then we have a 3h plus 3h, so plus 6h, and then plus h squared. So all of that is coming from that 3 plus h squared, and then we have subtraction with just 3 squared, which is 9, all over h. All right, we have a positive 9 and a negative 9, so those just turn into a 0, which means everything we have left in the numerator has an h involved, which is exactly what we want. So let me go ahead and rewrite that one so that we can really see the calculations here. So we have a 6h and then plus h squared over h. And there's a few ways to think of this in terms of cancellation. So in that last one, I just saw that I could take one h out of each piece. If it's helpful, you can factor the numerator so that we have a common factor of h. So I could write that as h times 6 plus h. And then with the cancellation, this can be a little bit clearer in terms of those canceling and just leaving us with the 6 plus h. So a few different ways to go about it, whichever one you're more comfortable with. And so we're evaluating this limit as h approaches 0 of 6 plus h. And now we're at a point that we can plug in h equals 0. So now we're going to take out that limit notation. We're going to have 6 plus h equals 0, which is 6. So, yeah, I didn't leave myself much room. So let's separate that out because all of this was to find m. This is the slope of our line. So we just found the m portion of our function. So we know the equation of the tangent line is y equals 6x plus b. But now we need to find what is b. And we can find it by plugging in this coordinate 3, 9. So we're going to have 9 equals 6 times 3 plus b, which means we have 9 equals 18 plus b. Subtract 18 from both sides, which should be a negative 9. So that means our equation is y equals 6x minus 9, and this right here is the equation of the tangent line. So let's take a look at this on a graph in terms of what we just did. So we have our function x squared. So we're going to have our parabola. Get this stuff out of there. We're looking at x equals 3, so we're looking at this coordinate 3, 9. And what we're doing is, let's see, we're all the way up here. We want to graph the equation of the tangent line. So all of that work to get out that value of 6 was to find the slope of that tangent line. But then knowing that we needed to go through this coordinate 3, 9, we could plug in that coordinate to find our y-intercept. So we found our equation is y equals 6x minus 9, and there's our tangent line. So we had our coordinate, found our slope using the derivative, and then using our methods of finding a linear equation, plug in a point to find the y-intercept. And there we go.